Welcome to this live broadcast of the celebration of the 80th birthday of Ramon Carbó-Dorca, Honorary Director of the IQCC, the Institute of Computational Chemistry Catalysis of the University of Girona. Ramon Carbó-Dorca was the first director of the IQC at that time. Since then, in 2013, this was merged with some experimental groups to become the IQCC to include the catalysis part. And as the start of this session, the first person to actually give some words is our rector of the university, Kim Salvi.
Good afternoon. I must say that on behalf of the University of Girona, it is a pleasure, a great pleasure to welcome you, members of the Institute of Computational Chemistry and Catalysis and friends of Professor Ramon Carbó-Dorca to his lecture ultima. Talking about Ramon Carbó is, in short, talking about the University of Girona. His unique figure, a free and dynamic, intense spirit, summarizes the origins and development of the university idea in detail. For a couple of reasons. First, he's a first-order professor in our university for his commitment to science and research, with an academic curriculum that few people can reach. His many stays abroad, his outstanding dedication to the renewal of studies on chemistry, physics, and the multitude of papers he has written and conferences he has organized, but also for his decisive contribution to the creation of the Institute of Computational Chemistry, today the IQCC, an extraordinary group of people. You guys make the UDG a great university, contributing to the building of a better society through your cutting-edge research and creating new promotions of undergraduate, master, and doctoral students. That's why Ramon Carbó's position as a professor emeritus of physical chemistry is a reference in the UDG for excellence, a situation that honors our university and that makes it even more relevant at this point in his last lesson. In addition, Ramon Carbó was one of the people who helped from the very beginning in the front line in the development of the UDG, contributing to our institutional history. And this is the second reason. Rector Pep Nadal wrote, "I would not be here and this university would not be what it is if there had not been people, many people, with an enthusiasm and a passion that became the engine of a story that has made us now here." Ramon Carbó is one of the professors who contributed to the UDG foundations, and without contributions like his, many of us would not be here. The UDG would not be what it is. The uniqueness of Dr. Carbó-Dorca is also articulated with his multidisciplinary desire, his humanistic delight, the progressive desire to reconsider the world we are in, outside the strict boundaries between science and literature. Writer, novelist, essayist, man interested in culture in a broad generic sense, lives as academic contributions, approaches to literature, deep ironies about the university institution, and it inspires us, above all, to have an intellectual ambition. He himself, a few years ago, explained a Zen approach that I think explains his character. On a rock, there are three banners, three flags that moved because of the wind. Three Buddhist monks discussed whether indeed it was the wind that moved them, or whether it was they who imagined that the wind would make them move. A fourth monk arrived, venerable and wise, and told them, It is your mind, the one that moves. The mind of Ramon Carbó-Dorca is a mind which moves and has made us all move. Today, it is the last lecture, but last lesson. But both in the lessons he has done and in the insight and theory that will certainly help us in the coming years, his mastery is still very much alive. On behalf of the university, it's a pleasure, Ramon. Thank you very much.
Oh, thank you.
Thank you very much, Rector, for this really nice words, nice overview of the nice person, the kind person that Ramon is, the importance that he has made for the UDG. I would also like to give a short background of the career of Ramon. Dr. Ramon Carbó-Dorca, he joined the Estudios Universitarios de Girona in 1986, quickly became a professor at the UDG and was one of the architects of the degree of chemistry and therefore of the Faculty of Science of the UDG. After a fruitful initial research stage as a laboratory of computational chemistry, on April 20, 1993, he became the first director and founder of the Institute of Computational Chemistry, the IQC. In 2013, the IQC fused with a number of experimental groups and became what is now known as the IQCC, Institute de Química Computacional y Catálisis. Note that tomorrow, it will be exactly 27.5 years ago that Ramon was creating the IQC and became the first director. Also note that a few days ago, on October 11th, it was exactly 25 years ago that the bylaws of the UDG were officially recognized. Within these bylaws, the IQC is one of the research institutes present within the UDG. And also note that quite soon after the merger of the IQCC, Ramon was recognized the title Honorary Director of the Institute. Although Dr. Carbó-Dorca retired in 2010, as Emeritus Professor of the UDG, he has continued an active research life, which has resulted in a long list of articles published in international journals. According to our IQCC website, so far this has been 227 papers, of which 83 since 2010, so after his retirement. This is quite an achievement. In total, these publications have reached over 10,000 citations from all over the world, according to Google Scholar, which means that there's on average 45 citations per paper. That is really impressive. Without further ado, however, today we're going to give a masterclass by Ramon, in which he will address one of the topics which he has recently developed and which applies to various fields of knowledge, particularly in quantum similarity, Boolean hypercubes. So please, Ramon, the floor is yours.
Hola. It's my turn?
Yes.
Well, no, thanks, Marcel. Thank you, Rector. Thank you, Miquel Duran, for organizing this apparently complicated connection of myself with the cyberspace. Cyberspace is made of hypercubes, Boolean hypercubes, of course. But perhaps before talking about Boolean hypercubes and their use everywhere in the subjects that I feel that they can be used, I can say that I was very pleased about this connection that the rector has made with one of the koans, the Zen Buddhist koans, about the big stone, the wind, and the mind. I like that the rector has also talked about me as a novelist. No, I'm not a novelist. My novels are poems, in fact, long poems about Girona. And Girona has influenced me from the beginning. I was born in one of the worst floods that the city has been covered by the water of the Ter and the Oñar. And in this sense, my connection as a poet, not a novelist, a poet, with Girona and with the old history of Girona connected with the Jewish heritage and the Kabbalah school, which has been made in Middle Age, Girona as one of the jewels of the Jewish thinking, probably related with the old Pythagorean school and numbers. Thus, my talk will be connected with all those things, perhaps more with the Pythagorean school than with the Kabbalah school, or perhaps with both. Who knows? Maybe you can feel this connection. Also, in some aspects, my talk will be connected with a literary source. Certainly, because Jorge Luis Borges has written about some idealistic aspects of Boolean hypercubes. His short tale about the Aleph is one of those things that you must keep in mind. His explanation about the library of all the libraries is certainly connected with Boolean hypercubes, because you will ask, perhaps if you never have read about all those esoteric things, what is a Boolean hypercube? A Boolean hypercube is the structure of the information in terms of bits that conforms this thought precisely. All the computers in the world at this instant, if we could put them into a string, the information of those, all the computers in the world, we can put this information into a string. That will be, at this very moment, just a vertex of a really big dimensional hypercube, Boolean hypercube. And all these just constructed with just two elements, a 0 and 1. A 0 and a 1, separately taken, is just a hypercube of one dimension. A two-dimensional hypercube is a square made by 4 two elements vectors, hey, vertices 0, 0, 1, or 0, 1, 1, 0, and 1, 1, and so on. A three-dimensional hypercube is an 8-dimensional vertex structure, three-dimensional structure. But in this way, you can construct whatever dimension hypercube you want. 4-dimensional, you have 16 vertices. N-dimensional, you have 2 to n vertices. And so what? You can put n whatever number you want. Why? Because with the modern computer, modern programming, you can construct any structure of as much as bits as you wish. But you can handle those structures which seems very difficult to handle at first moment. But once you get a little bit of idea of what's that, it's easy, much easier than write a poem. Much easier. For example, I imagine other structures, other geometrical structures. Tetrahedron, for example. A three-dimensional tetrahedron can be from this point of view, binary point of view of 0 and 1, can be constructed, perfectly constructed, in two ways into a three-dimensional Boolean cube, but no simplex, which is the name you can give to n-dimensional tetrahedron, can be inserted into a hypercube. Just the 3 dimensions can hold together a cube and 2 tetrahedrons. But this is one of the peculiarities of this problem. You can put your foot into the ocean of the complexity which you can find in Boolean hypercubes. Let's see. A hypercube, any hypercube of any dimension, I imagine even infinite dimension, can be defined by 2 vertices. One is the 0 vertex, where all the bits in this vertex are zeros. And so it's a trivial one. It seems that the other one, which can be described very well without problems for any dimension, is the unity vertex, which is the vertex which is from the distance point of view, whatever distance you define, is far away from the 0 vertex. Is the unity vertex, where all the bits of this vertex are ones. 1, 1, 1, 1, 1, and that can be up to infinity. While the 0 vertex is obviously or can be associated to the number 0, the natural between quotes, because it's not clear if 0 is a natural number or not. The unity vertex is related to a number which has the name of an abbé of 18th century, contemporary of Fermat precisely, called Mersenne. Any vertex, unity vertex, can be translated into a natural number, which is a Mersenne number. Mersenne number is simply computed as 2 power n minus 1. This minus 1 is essential. For example, in 2 dimensions, the Mersenne number is 3. In 3 dimensions is 7. In 4 dimensions is 15, and so on. Some of the Mersenne numbers are prime numbers, like 3, 7, not 15. But 31, which is the Mersenne number associated to dimension 5, I guess, is prime. But guess what? The largest Mersenne number, which is a prime number, is the largest prime number which can be obtained in this way, and has been obtained very recently, because to obtain 2 to n when n is of the order of, I don't know, hundreds or even thousands, minus 1, it was very difficult formerly, not now, with the computing facilities. If you go to Wikipedia and ask for the prime Mersenne numbers, you will get the list, and you will find, and you will know what is the largest prime number, which is the largest Mersenne number computed up to now. But all those Mersenne numbers, being prime or not, translate into a binary vertex of some Boolean hypercube as the unity vertex. I don't say unit because it can be confused with the unit matrix, let's say, but unity because you can write it as 1, but in boldface, to differ from the unit matrix, for example, which is an I in boldface. All the other vertices can be also discussed and used. They can be used immediately as with a simple transformation into a generalization of the concept of sign. What is the sign? Is +1 or -1 in the scalars. But what is the sign of a vector? What is the sign of a matrix or a tensor? A numerical one is very easy to construct. It is a vertex of a transformed Boolean hypercube, considering now the ones and zeros not like a binary numbers, but like rational numbers. I'm saying rational because when we think about computing, they are not real numbers. Pi is not real. It's a rational number from the computing point of view. The E number is not computationally speaking, is not a real number, it's a rational number. So 1 and 0 can be rational numbers. So you just need to imagine a Boolean hypercube of the any dimension, and then compute, considering the ones and zeros as rational numbers, compute the centroid. What is the centroid of a hypercube of any dimension? Is the unity vertex, the 1, 1, 1, 1, 1, 1, divided by 1/2. Simple, very simple. What is this 1/2 of the unity? Is an homothethy of the unity number, the unity vertex, excuse me. The Mersenne vertex also you can talk about, because translation of the binary unity vertex are Mersenne numbers. The centroid, as I told you, is the homothethy 1/2 of the unity vertex. So, and if you take the centroid and subtract this centroid from every vertex of the Boolean hypercube, not Boolean now, will be, let's say, rational n-dimensional hypercube, you get a new hypercube whose vertices are constructed by -1 and +1. So any vertex is the signature of any vector of the appropriate dimension. But matrices and tensors can be reordered as vectors. So a hypercube transforms into a signature hypercube in this way, this simple way, can be considered as how one can put signs in vectors, matrices, anything which can be expressed as a set of ordered numbers. You can consider any vector as a vector without signs. Any vector, any matrix without signs is a vector of a space which I call semi-space, but it has been called orthant. But orthant is a esoteric name. It's much better to say semi-space, because semi-space is made, the summation is made of a semi-group which don't accepts negative elements. So if you multiply every element of a matrix, of a vector, of anything, by one of the appropriate dimension vertices of one of these signature hypercubes, then you have any vector you can construct from a completely positive vector. More than this, if you do not admit zeros into a vector, then you can order the elements of a vector from the minor one to the biggest one. A vector ordered in this way with its zeros is a perfect vector. From this vector, say n-dimensional, you can make a permutation of all the elements, and you have n factorial vectors which differ from the original one, but they are related. And plus to this, you can put any signature of the 2 power n signatures you can construct. So from a very simple mathematical construction, which is a perfect vector, say a vector which the element 1 is less than the element 2, and that less than element 3, and so on, you can construct a huge amount of vectors which are completely different from the first one. And that's related with Boolean hypercubes. A perfect vector can be supposed connected with the Mersenne vertex, the unity 1, 1, 1, 1. And from this, you can construct 2 power n different vectors using the signatures. And plus, you can make permutations, and you can have n permutation vectors. Those are simple possibilities. But maybe the most interesting property of Boolean hypercubes is related with the possibility to construct the natural numbers associated to the vertices of a hypercube. So you start with 0, with the vector 0, 0, 0. You follow with 1. All this vertex, all the elements are 0 except the last one, which is 1. I chosen the less significant number on the right and the most on the left, as we write the usual decimal numbers. So, and then the number 2, which is the 0, 0, 0, 1, 0, and so on and so on. So from the 2 power n vertices of a Boolean hypercube, you can construct from the 0 to the Mersenne number at the quadrilateral. Well, and you say, well, come on, that's trivial. It's not so trivial, because Boolean hypercubes can be concatenated. Concatenated means that you can take another hypercube, whatever dimension, and combine this hypercube, say, of dimension m, with a hypercube of dimension n. And what is the result? A hypercube of dimension m plus n. So I imagine the following. You have n-dimensional hypercube, and you concatenate simply with a 2-dimensional hypercube. That is, with a 0 and a 1. If you concatenate it, the concatenation is different if you do it from the left or from the right. Remember that left digits are the most significant. If you concatenate from the left, you put a 0 in front of all the vertices of the hypercube. And what you have? Exactly the same vertices of the hypercube of n dimensions, but belonging to a hypercube of n plus 1 dimension. And what happens when you put an 1 to the vertices of a hypercube of n dimensions? You have 2n vertices which are not contained in the old initial hypercube of n dimensions. In this way, you construct a new set of the binary numbers, which can be transformed into a sequence of natural numbers, which are not contained in the old numbers of the n-dimensional hypercube. What's the meaning of this? The meaning of it is that this is a way to rationally construct natural numbers. You start with the 2 power n numbers from 0 to the Mersenne number of n dimensions, and you can continue with 2 power n, which is the first vertex, which is not contained in the n-dimensional hypercube. So you duplicate in such a manner information from the old information you have with exactly the same amount of information, but different from the information you have. But look at that, just adding 1 bit. What is the meaning? What is the rational meaning of that? The rational meaning is that whatever dimension you have constructed information, just 1 bit creates exactly the same amount, different from the former one. That can be really connected with an old theorem in the 20s of the past century, explained by Gödel, and which can be translated into the fact that no theory can be complete, because when you construct a theory, you write it somewhere, you film it, even you do whatever you want. When you have this theory together, you add 1 bit, you have a completely new set of information, which has something to do with the former information, but is completely new. Completely new. So no one can claim that have the absolute knowledge about anything. And maybe that can be associated to us, to all of us as scientists, to be a little bit humbler than we used to be usually when we speak. Just a bit can change many, many aspects of the knowledge. No theory can claim to be complete. That was when stated by Gödel, not by me. I am just the shadow who has found this connection of the Gödel incompleteness theorem with Boolean hypercubes. That has been, for some scientists of the time of Gödel, a terrible joke, a bad joke, in fact. For example, Hilbert was thinking that mathematics could be a perfect body of knowledge, and the humble Gödel theorem has teach him that cannot be true by any means. So you see, Boolean hypercubes can have really surprising results, very surprising results, like this one. Another one is our possibility to define what is infinity. You know that also a little bit in the same period, maybe earlier than Gödel's theorem. That was a mathematician who has been talking about the possibility that infinity, as we thought about, could be not the last thing about the biggest amount, in this case, information we can have. Because I imagine an infinite dimensional hypercube. And according to Cantor, we can say that this infinity can be called, instead of infinity, Aleph 0. Aleph is the first letter of the alphabet, the Jewish alphabet. But what happened? We know that we can concatenate hypercubes. Why not? We can concatenate an Aleph infinite dimensional hypercube with another Aleph infinite dimensional hypercube. The result cannot be an Aleph 0 infinite dimensional hypercube, but something else. Because if I told you with a unique bit information is duplicated, I imagine with the multiplication of information you can have, concatenating two Aleph 0, two infinite dimensional hypercubes cannot be infinite dimensional. Is something else. Is an Aleph 1 Boolean hypercube, and so on. You can add another Aleph 0 here, and you have an Aleph 2 Boolean hypercube, and so on and so on. That's kind of mind-boggling idea, but that's the way it is. You just think a little bit about that, and you feel what's going on. So just we have very simple thing, a Boolean hypercube. Just you can complicate it a little bit with the dimension, but that just means that you have more vertices, right? So what? In a three-dimensional cube, in this case, you have 8 vertices. In a 4, 16, next 32, and so on, so on, so. And so what? Note that usually the structure of the information handled by computers is made by 8 bits, a byte. That's a vertex of an 8-dimensional hypercube. Simply as that. What is in the memory of the computer which handles this conference is a huge dimensional hypercube. But in every instant, you have the exactly a vertex of this n-dimensional hypercube as a carrier of information. But let's go a little bit literary now that we are in the Cantor-like infinity, different infinity structure. Borges, I imagined two things. One is this Aleph, which constitutes precisely a very nice short tale from him, where someone discovers that somewhere there is a point, a unique point, where everything is included. Everything you can imagine. The universe, anything is included in this unique point. That's an Aleph. But probably he was joking, thinking about the infinities of Cantor. But we can construct Alephs. The centroids of a hypercube of any dimension is an Aleph. It contains the average of all the vertices of a Boolean hypercube, taking into account that the binary numbers can be transformed into rational numbers. But how will look a centroid of an Aleph whatever hypercube? It will look like 1/2 of an Aleph infinity number of ones. So we can imagine how an Aleph could be. And in this Aleph, it will be concentrated, all the information which can be constructed by the humans in form, of course, of binary strings of any dimension. Borges also, I mentioned, or in somewhere in another tale, explains the existence of a library which contains all the libraries of the universe. That is, all the information which can be constructed, past, present, future. It will be a book, for example, in this library, which is blank, zero. Another book which has only one bit, and so on and so on. But maybe an infinite number of books will have the almost infinite number of creations of the human mind, the human knowledge. Present, past, future can be all together into a Boolean hypercube of the dimension you can need to construct that. That's not the only thing. I am a chemist and I should talk a bit of chemistry. How about chirality? We know that proteins, peptides, are made of levo amino acids. Sugars are made of dextrose sugars. But how about other molecules which have more than 2 or one possibility. I imagine a peptide, I don't know, insulin, angiotensin. All the amino acids are level amino acids, but change one of them into a dextro. And if you change only, say all are level, is the same as to say, I imagine, I don't know, a 10 amino acid peptide. All the elements are level, and you say level for me is the same as to say 0. And dextro is the same as to say 1, or vice versa. That's arbitrary. Our 10 amino acid peptides will be like the vertex of a 10-dimensional hypercube. In the moment that you change one of those level amino acids by a dextro, that will be any of the rest of the vertices of the 10-dimensional hypercube. If you construct the dextro peptide, all the amino acids with dextro, that will be the Mersenne vertex, precisely. Then any of those peptides can be, from the point of view of chirality, transformed into a natural number, taking into account that 0 is a natural number. 0 will be the peptide with all the amino acids level, and 2 power 10 minus 1 will be the peptide with all the amino acids dextro. But what happens when your basic things are more than 2? We have in biochemistry a very nice example of that. The DNA is constructed with, say, forget about uracil, with 4 bases. But now there are many, not many, but some scientists are working with DNA, introducing in them bases which are not the 4 well-known DNA bases or RNA bases. They work with 6 bases, but I had been thinking about that. I even published a small paper saying that 6 is not a good number, but 8 will be a very good number, because 8 will be the vertices of hypercube, while the 4 bases are the basis of a 2-dimensional hypercube of square. 8 will be the vertices of a cube, and that means that the information of this DNA constructed with 8 xenobiotic, half xenobiotic bases could have exactly the same amount of information as our 4 bases, 64 precisely. And the codons, instead of 3 bases, with 2, that will be sufficient. So in this way, one can construct DNA or biological objects, living objects, which will need only codons with 2 bases, stable, much stable from the point of view of mutations than we are, because our 3 bases codons are subject very errors, more errors than if we have columns with 2. And I don't know, and I could continue talking about that. But just I want to see that, to tell you that we have, not myself, but with the help of people from Spain, from Castilla-La Mancha precisely, very old friends. One of them deceased pitifully, to try to see if Fermat's theorem can be extended to other dimension. Fermat's theorem is a 2-dimensional theorem. It seems that to show Fermat's theorem has taken mathematician Wiles, has taken a paper to write, has forced to write a paper of 100 or more, maybe 150 pages to demonstrate the apparently simple Fermat's theorem in 2 dimensions. But we were questioning if how about 3 or 4 dimensions? I can tell that based precisely on the construction of natural numbers via Boolean hypercube structure, we are, after a lot of supercomputation, we are able not to prove a 3-dimensional Fermat theorem, but to conjecture that in 3-dimensional Fermat theorem, or an equivalent to Fermat theorem, is also possible. What about the 4th and 5th dimension? They are curious behavior of natural number spaces, which will be difficult to discuss here in a few words. So I think that with this, maybe I can finish, but no, I can finish with more. In fact, Fermat's theorem can be extended to any dimension if one takes the power 2. That means that any vector made of natural numbers without zeros, summing the squares of those numbers, whatever dimension, there always be some of those vectors which equals another natural number squared. That's an obvious extension, because all those dimensions squared provide with a sphere, n-dimensional sphere, and it seems that numerically you can extend Fermat's theorem with the power 2 to n dimensions, in the same way as you can extend the theorem in dimension 3, power 3. So I think that I will stop here. Boolean hypercubes have been used also to discuss multivariate logic and many other mathematical conjectures, but that will probably need much more time than the one that I used now, and I will finish. Thank you, everyone. But I saw that underneath my talk, there were congratulations from even from Ecuador. So please be aware that I have been aware also that you were telling me congratulations. So thank you very much to everyone.
Thank you, Ramon. Thank you for an inspiring talk. A really nice and masterclass on Boolean hypercubes and the effect this has on chemistry, biology, computer science, but also the daily life, also the DNA, and how we can actually, with a larger basis, we could actually get the same information with only two codons. The one thing which I like the best on your part on the masterclass is the one on the infinities. Infinities where you cannot just add two infinities to get the same infinity. You have different infinities, and this brings me back to a question of my nephew.
That looks weird, but you don't add two infinities. You add two to some kind of infinity multiplied by two to some kind of infinity.
Yeah.
So the information content of the result is not exactly the same as in the original infinity. It's a little bit difficult, but that's in fact that's inside the reasoning of Cantor. In I think that he wrote this at the beginning of 20th century, on the end of 19. I cannot remember exactly, but that's the trick is that you don't add or multiply or whatever two infinities, but two to the power of the infinity. And in fact, you concatenate vertices of an infinite hypercube with the infinite vertices with the infinite hypercube. And the result is not an infinite of the same way as the original one. That's something else. Well, it's not so clear. It seems that Cantor has been, ideas have been discussed very much, but to me, it's maybe an ancillary explanation of why Cantor can talk about different kinds of infinities. This Aleph 0, which is the normal that we think with infinity. Aleph 1, which is the concatenation of two initial infinities. Excuse me, but that's maybe needs a more discussion in deep about that.
Before we go to the question,
like me, but I know.
Before we go to the scientific questions from the audience, I just wanted to you already mentioned Ecuador, but there have been people from all over the world. So we have Patrick Bulting from Ghent, Jordi Ramon Quintana from Sarriá. Then you have Angulo from Granada, from Oviedo, Donostia, Siberia, Barcelona, La Habana, Madrid, India. This masterclass is all over the world.
Even from Novosibirsk.
Yes.
I have a very good friend there who has been precisely invited at the IQC, the old IQC.
The old IQC. So there is a talk by a question by Miquel Duran. Ramon, you mainly use Hypercube vertices. How would you use Hypercube edges?
The vertices, well, in fact, more than vertices, but may be useful the distances between vertices. I use the distance between vertices between the 0 and the Mersenne vertex, which is the largest distance. The edges are not so interesting because means that they connect two neighbor vertices, and that's in hypercubes and Boolean hypercubes is the same everywhere. It's not more the geometric construct than the mathematical construct that's interesting. For example, distances between one vertex and everyone else, then it's very interesting because you can have 1, 2, 3, and so on up to n. No, and that allows you to order in some manner the vertices into classes. All the vertices which are at a distance 1 from everyone. All the vertices which are at a distance 2, and so on, and so on, and so on. Well, and you can use these to order elements as we have been doing in molecules using quantum molecular similarity. You can connect those things. I didn't talk about that because it will be a subject of a talk by itself.
Also see that Andrea Savin was also connected. But Miguel Sola asked, is there any relation between the Boolean hypercube theory and the Shannon theory of information?
Well, excuse me, I didn't understand that.
Is there any relation between Boolean hypercube theory and the Shannon theory of information?
And the what?
The Shannon theory of information.
Yeah, of course, but I didn't make the connection. No. But of course, if you have information, any kind of information which can be transformed into a binary elements, which is everything from the photos sent from Mars to the most exclusive article about anything from any book written. This information is made in the form of a vertex of a hypercube, as I told you about the library of all the libraries, where this library contains of the books written in the past, now, and to be written in the future. That's the connection. Everything is information. Of course, you can use Shannon ideas on the hypercube vertices, sure, but I have not done that. I don't know. Don't ask me why, because my mind was going on another path. No, that. But it's a good idea. Maybe
for the next 10 years.
Pardon?
For the next 10 years to work on.
I don't know. I don't know. Maybe I will write another book of poems. I don't know.
Yeah. I see there's no other questions from the audience, so I think we should move on to there's a number of people that also wanted to contribute to this event. And the first of these people is the Dean of the Faculty of Sciences, Jesus Colprim.
Hi, Ramon.
Hello.
I'm pleased to meet you again here.
Long time no see you. Huh?
Can you see me? Yeah?
I've been you for a long time, not now. Now I see you.
Okay. So it was more or less about 30 years ago that we meet for first time. You probably don't remember, it was in 88. You were my professor of computational chemistry in second degree.
My memory is very short.
I'm not sure about that because probably you remember some kind of a small pic that was delivered to you.
A small what?
Pic.
Speak
Un porquet.
to me?
Yeah. Close to Christmas. You asked for a hand.
No, I don't know what do you mean. I don't. Maybe I.
We can discuss afterward. Don't worry.
Because of that, I am going deeper and deeper.
Don't worry.
Tell me again. I didn't understood.
Anyway, I would like to wish you a happy birthday today from a fan point of view. And I have no doubt that your scientific point of view it's really outstanding and brilliant. And probably 80 years old is not so much, unless you compare to the computational times that we have 50 years ago, because of the times of computing were so slow and now they are so fast, no? But what is important is that computational times, it's nothing compared with brilliant minds that you run. So I have no idea about Boolean hypercubes, but I can say without any doubt that your scientific background and contribution to quantum mechanics has been a step forward, like an example for the current and the future scientists in the world. So, Ramon, et desitjo realment un feliç aniversari i tinc ganes de tornar-te a veure per la Facultat de Ciències, no?
Ja, sí, amb el Covid-19 penso que trigarà una mica. Yeah, I would like to come back one day, but let's hope that this problem with the virus will be finished, and maybe I will come. Yeah, sure, for sure.
I will be proud to receive you at the faculty again.
Yes, thank you very much about that.
Thank you, Kim.
I will look forward to come back.
Yep.
If I live sufficiently long.
Thank you, Jesus.
Thanks.
And then we move on to Michael Solá, former director of the IQC in that time.
Okay, thank you, Marcel. And let me start this intervention with telling an anecdote that I have about Ramon. And I have to say that the first time that I heard about him was when I was doing my bachelor, so some years before 1986, and it was when I read an interview to Ramon in the newspaper La Vanguardia in a series that was called Nuestros Cerebros. So it was a series that was referring to brilliant Catalan scientists. And I remember the title of this interview was "When I Get Angry, I Dig the Ground Hard." So I was very impressed. And I make a photocopy of the interview and I put it in my room. So instead of having a poster of AC/DC or Iron Maiden, I have one with Ramon. I don't know if you could believe it, but it's true. And first time my mom saw it, she asked me, "Who is this guy?" And I tell him about the story about Ramon, the things that I know from the interview at that time. I have to say that I arrived to the IQC on February 1993. And at that moment, Ramon was the unofficial director of the unofficial IQC. And he became the official director of the IQC a few months later in April 1993 and remained director till June 2004. I had the great honor to succeed him in the direction of the IQC for 3 years till June 2007. And now I'm speaking as one of the ex-director of the IQC. So one thing that I want to tell you also is that in the first session of the governing council of the IQC, Ramon said that among other things, the IQC works is on the generation of artificial intelligence software to the application of molecular engineering. So now everyone talks about artificial intelligence, but Ramon was doing so in 1993. He has been always a pioneer. It's been in all the fields that he has, let's say, lived. And let me refer to a sentence that is often attributed to Isaac Newton, but it was formulated some centuries before by philosopher Bernard of Chartres. And he said, "We are like Thorbus sitting on the shoulder of giants. We see more and things that are more distant than they did, not because our sight is superior or because we are taller than they, but because they raise us up, and by their great stature add to ours." Ramon has been one of these giants. I think it's very important that we pay tribute and recognize the work of those who has preceded us, and Ramon had to dedicate a lot of energies to build the IQC from scratch. For the rest of us, like me and many others, it was much easier to progress scientifically because everything was running smoothly. So let me recognize the work of Ramon and saying that we are very grateful to you for your leadership and guidance and for being a scientist of reference for many of us. Thank you very much and happy birthday to you, Ramon. And just to finish, let me remember that together with Gernot Frankin and Tamoy Chakraborty, we are preparing a special issue of Theoretical Chemistry Accounts to celebrate the 18th anniversary of Ramon. So please send your contributions before 20 December 2020. Thank you very much.
Thank you, Miguel.
Thank you. May I say something?
Yes.
What you say about the something in La Vanguardia?
It was. I have to find it, but okay. I don't know if I make a copy of this, but I don't know if I have it yet. But it was an interview in a section called Nuestros Cerebros. Do you remember? It was 18.4 or 18.5, something like that.
In those times, nuestros cerebros were so few.
Yeah, but you were there.
I consider it a genius. But I don't remember this
the sentence, the main sentence was cabo la tierra con fuerza. Cuando me enfado, cabo la tierra con fuerza. Something like that. Yeah, it's for sure.
Make a PDF and send it to me.
Yeah, if I find it, I will do it.
And another question. I start using artificial intelligence in 1979, 78,
wow.
and published the first paper based on that in 1980, precisely.
Mm-hmm.
How similar is a molecule?
I remember this paper, yeah, of course. Thank you, Ron.
I think that arrived to 800 and so quotations.
Mm-hmm.
Just
40 years ago.
Congratulations, Ron.
But there is glad to be a brain of country, or brainless country, maybe.
We move on to Luis Blancafort. He was the one, the director after Miquel Solà. If he's there, he's not there. So we move. Sorry, Ramon. We move on to the first administrative person for the IQC at that time, Pilar del Acebo.
Hola, bona tarda, Ramon. Per molts anys. Com estàs?
Bé, ben fet.
Bé. Va. Com que jo he parlat de la part més acadèmica, jo parlo de la part més personal.
Okay.
Dos moments. El primer, el dia que et vaig conèixer, jo anava perquè m'havien dit que un professor de la universitat...
Maybe can you do it in English, but because your English is better than mine.
Well, I will try. Okay. So the first time I met you, it was in 1991. I was looking for a job and I was working as a hostess Congress hostess, and somebody told me
that I remember.
that you need someone to help you with the Congress, chemistry Congress. So who spoke English? So I went to see you. You asked me how was my English. I said, well, okay, not so bad. And you said, okay, you start tomorrow. I said, oh my God, he's so confident. He's so sure of me. And it was all the time was like this. I remember that I used to write some letters and you signed it just without reading. And it was, oh, perfect. Maybe I could raise my salary sometime.
And you did quite well anyway.
Well, thank you.
And and more than this, you suffered my bad temper for many years.
No. This is just how you look, how you could like to look, but you are so tender inside. I never had any problem with you.
Yeah.
Well, and another moment, yes, when you say everybody for breakfast, and all the people in the IQC, in that time, 5, 6, 7 people, the most, we all finished what we had in between hands, and we went all together to breakfast with you, and all as not as a family, but as a very nice group, I think. So I remember these moments very, very nice and very sweet, and I congratulate you for your birthday, and I wish you happiness for all the life you have behind ahead.
Thank you very much. I can add to your nice speech that probably the Institute of Computational Chemistry could have not been as it is now without you doing all the job and showing your passions in front of my impatience. So, thanks. I think that the old timers at the Institute shall be in accord with that we must thank you very much about this. More than me, I was just sitting in a chair doing my thing, but you were doing the worst work around. So no, thanks very much.
Well, it's your birthday. Thank you very much.
That you went away, but that's life. You need to be in a better position than that one. So
yeah, they have you in my heart.
But the one who followed you also did a real very good job too.
Sure.
Different but similar.
Thank you, Pilar, for your contribution and your nice words to Ramon. And indeed, what Ramon is saying is true. The administrative part of the Institute has been, is, and will be always the one specific part of the Institute which makes that the Institute goes well and does not go well. So thank you for that part. We haven't met at that time, but from as I've heard, it was a nice job as well. Thank you.
Thanks.
Now we move on to Luis Blancafort, the also former director of the IQC. There was a slight technical error before. Luis.
Okay, thank you. Well, congratulations, Ramon. Happy birthday. Of course, as the Institute director of the Institute, I quickly became aware of your importance and your great role in the Institute in creating it. And we are all very thankful for that. I think that also your birthday is an occasion to celebrate the Institute in a sense, because it has developed a lot since you put the first stones, and I think this is the result of everybody's work. And I actually I actually knew Ramon already before I joined the Institute because as a freshman in 1984, on my first day at the Institut Químic de Sarrià, I had the opportunity to enjoy a lesson by Ramon. So we had a full course on algebra. And on the first day, he taught us the Greek alphabet. So maybe that's not exactly what you expect, but in retrospect, I think that was telling us as students a lot about the person of Ramon. And well, I also want to congratulate Ramon for his activity and in particular for maintaining it until now. And well, I want to ask the future director of the IQCC to start organizing the party for the 85th anniversary. And so congratulations again, Ramon.
Yeah, well, thank you very much. Yeah, I know that you were a student of mine at this time, but I cannot remember which marks I put you. I don't know if they were good or bad or half, but thanks for your words.
As usual, when they are good, they are the merit of the student. When they are bad, they are the fault of the professor. So.
Yeah, but there is another point which I want to say. That's to say, to celebrate the 85th anniversary, why not the 90? No? Why not the 90? Maybe.
Well, because I think that time is linear.
I will have.
So I prefer to think about the 90 after the 85.
Maybe I'll have 10 papers more on Boolean Hypercubes applications, so I can bore you a little bit more. So, but anyway, thanks very much. Let's hope that even the 81 will be a very nice point to arrive. So, but
okay.
Don't celebrate. Let's wait on the 85.
Yes. Thank you, Luis, and we'll make this homework for the next director. My term ends at 23, so it will not be me who will be organizing the 85th birthday. And now we move on to Silvia Simon, Directora of the Cathedral of Science Communication.
So, can you hear me? Yeah. So, congratulations again, Ramon. I told you in the backstage, but I think that it's time just for make it public. Congratulations for your birthday. And just coming back, what Jesus, the dean said, I remember the little pig. I was in the previous course, and I remember all these guys. They were kind of bad guys that they gave you this very nice pig. But it was a long time ago, 30 years ago. It was in the Casa de Cultura. Yes. So, and I was attending your course on physical chemistry, of course, and as I wrote in somewhere, it was really a very complicated course, very difficult just to follow, but it was incredible to just to sit down there and hear you. I don't know why, but the way that you have been explaining us some integrals or something, then at the end I realized that it was not so magic what you were talking about. It was real quantum chemistry. Well, so I'm here in just to talk or just to explain that something about your scientific community, your life in the communication of science. So you always start with imagine an n-dimensional hypercube. So someone who starts the sentence saying something like this just can have a very large imagination. That means that he can write many things, not only quantum chemistry, not only mathematics, but also Ramon has been writing many books. He has been participating in many articles in newspapers. So just bringing science, what it's called complicated science, to the general public, which is great. There are not many scientists in the past 30 years that have been contributing in this sense. So I just wanted to also to say that when we met 1 hour ago in the backstage of this talk, I asked him about how was the COVID going on, and the first thing he told me is just make the similarity, why not, between hypercubes and the peptides. So really, it's a very, he has a great mind for just comparing and just to bring this very difficult concept of hypercubes, Boolean hypercubes, to normal science, let's say. So I just want you to congratulate and to ask you to write something. I will ask you to write a dissemination paper, or just to make a short talk, not for scientists like us, but for maybe high school students, just to explain them what are these Booleans, hypercubes, and how important are they, which I think it will be very easy for you and very difficult for me. So thank you very much, Ramon, and keep on talking like this and imagining like this.
Yeah, thank you. I remember. Can I say something?
Yes.
Because for me, will be always the game. So we had been together in Tokyo, in Japan, at the Chirality laboratory.
Yeah.
Among other things, from time to time, someone could make a pot of coffee by themselves and all the other students around. But only when Silvia was making the pot of coffee, everyone was drinking this coffee. Probably that was because it's an old Japanese idea that coffee made by men don't taste good. That when done by a woman, everyone was drinking the coffee. So thanks, Silvia, for the nice remembrances, the talk about myself, which I don't know if I made it all that, but among other things, by your nice Japanese coffee.
Thank you, Ramon, and congratulations.
Yeah.
Yes, thank you, Silvia, for your nice words on Ramon. And we move on to Joan Miró. There it is.
Congratulations, Ramon.
Thank you.
Excuse, but I talk in Catalan because we are friends, all friends, always in Catalan. Vaig conèixer en Ramon a la primera reunió de química quàntica espanyola organitzada per la Real Societat Espanyola de Química i Física a Madrid, si no me'n recordo malament, a l'Institut Roca Solano, i va ser una mena de celebració, de manera que quan anys després en Ramon va manifestar la seva voluntat de traslladar-se a Girona, ho vaig celebrar com si fos un regal. La veritat és que ens va aportar amistat, empenta, un clima de treball modern i molt actiu i una gran, i en certa manera va donar fama als estudis de química de Girona. Jo espero, això del 69, el 1969, és de fa molts anys, many years ago, it's like a song. Jo espero que puguem celebrar molts aniversaris més. I wish that we come together to celebrate new anniversaries with Ramon and across the time and the space. I said that we wait for you, Ramon.
Oh, what do you say?
We'll wait for you, Ramon, as the song, the Cherbourg song.
Well, let's hope so. Oh, thanks, Joan, for your kind words. So let's hope that we all met again somewhere in the future, if that exists. Anyway, for you probably, for me it's not so sure.
Yes, thank you, Joan. And now we move on to the younger generation. So we move on to the winner of the Catalonian National Award for Young Talent, was awarded last week, Silvia Osuna.
Hello, hi, Ramon. Well, being the youngest in the list, I don't have that many anecdotes as my older colleagues have. But what I can tell you is that when I first started the PhD, I remember that we celebrated your 65th birthday with a great party, with a lot of great. I was really, really impressed. And then as a funny story, I also remember that the first conference I attended in Ghent, apart from the science, I also had the opportunity to get a ride with your convertible while listening to some tangos. So it was funny. Well, apart from these anecdotes, I would like to thank you for creating the institute we have right now and that we are really proud of. Also, thank you for the vision you had to create the Girona seminars. So we are still all enjoying the Girona seminars, and they have really contributed to put Girona in the map. So the research done in Girona is known everywhere. And also, Ramon, congratulations for the great talk you gave today, but not only for today's talk, but all talks that you always give. They are really inspiring and motivating. And yes, and happy birthday. And I wish you a happy and healthy 80th birthday. So thank you and congratulations.
Well, thank you. Thank you for your speech, and more than you congratulate me, I must congratulate you for this nice prize. Personalitat is not very good giving money, but I hope that they have given you some, no?
Yes, they have. Thank you.
The problem is that maybe we give you this prize, but you owe us 1,000 euros. So you must pay them for the prize, probably. No. I hope that they have paid something for you, at least the travel expenses.
No, they have. I cannot complain.
Oh, good then. So, yeah. Your work. Yeah.
Thanks, Ramon.
Yeah.
Thank you, Silvia. And now we move on to the almost last speaker, which is someone you know really well, Emily Basileum.
Hello. Hello there.
Hi, Ramon. How do you do? Hi.
We are getting older.
So I will explain a very short anecdote related to your course, doctorate courses at the University of Girona. When I was very young, you started a very, let's say, revolutionary pedagogical innovation, because all the people has to know that all your courses were developed not at the classroom, but at the bar. There were the classes were very interesting. Every afternoon we were to the bar, and the courses were very interesting. So I'm so glad to see you again, remembering now this speech, new scientific concepts, and you see that you are still here, as we say in Catalan, al peu del canó, at the foot of the cannon, always in the middle of the scientific war. So my desire is that you have to never stop your scientific anxiety, and you're always, let's say, hyperdimensional and novel productivity. Per molts anys.
That's all.
That's all.
Well, thanks. I must remember two things to you. The first one is that one of our papers in the journal Mathematical Chemistry is one of the papers most read in our list, and yours and mine list. More than 1,500 readings, no?
Gaussian product theorem.
And then also I read a paper of yours, a recent paper of yours, that you use Boolean hypercube vertices to describe molecular properties. So, but I must remind you that in doing so is the same as to put a natural number, just a natural number, to every molecule. A big one probably, but because I think that you use 300 dimensional or so, no, or more maybe.
Yeah. Because
So
of the descriptors, yes.
More or less over 300 possibilities you have to numbering one molecule. Yeah. Well, congratulations anyway.
Thank you.
And up to the next talk.
Okay.
Of course.
Yes. So these are probably the two most intimately connected scientific part of Ramon's scientific career with Emily Basileum. So it was appropriate that he was the last person to actually congratulate you in person. Well, in person, online. And now, as a director of the IQCC, the current one, I would like to congratulate you in name of all the people, all the members of the IQCC, current and past. Congratulate you with your 80th birthday. And I would also like to, I have to play a bit, because we have been preparing a little gift for you, which is an online way of celebrating this day with you. And let me just...
Virtual cookies, virtual booze.
If everything is done correct. Can you now see the screen? Yes. So this is a Jamboard where we have been opening up for many people to just write something, dedication to you, to your 80th birthday, of course, but also just in general, what you have been meaning for them in the last decades within the IQCC, but also all over the world. It's not just here in Girona that you have made an impact, in which you have inspired people. As we have seen in the comments during this masterclass, they have been from all over the world. You have been inspiring people, all kinds of people that would like to have you back where they are, to actually talk to you, to discuss with you on all kinds of different topics. If it can be DNA, hypercubes, all these things they would like to discuss with you. So you can read this in more detail in the coming time. And for those who are following this now, if you also want to write something in this Jamboard, please contact me at director@udg.edu, where I can actually give you access to it, so you can actually add some text of your own. And with that, we actually come to the, of course, I'm not the final speaker. The final speaker should be Ramon on his own birthday. I would like to give the floor now to you, Ramon, to give the final words of this session of the masterclass. If you want to say something else.
Yeah, thank you very much to provide me the occasion to deliver this talk, which I thought which will be a very interesting way for me to celebrate my 80th birthday. If anyone is so full to celebrate such an old age, but maybe should be an occasion of do not celebrate, but to celebrate, as Lewis Carroll says, every day of not anniversary. That's will be a very good celebration, but that will be too much, no? That you accept every day one talk about Boolean hypercubes or even more abstruse concepts, and we're forced to hear what I'm trying to say. So anyway, thanks to the Institute, thanks to you, Marcel, thanks to Michael Duran, who has brought all the gear and knowledge to make this possible. Thanks to the University of Girona, and thanks to the gods who had been so nice to allow me to live up to now. So see you next time, perhaps. And thanks.
Thank you, Ramon, for this nice masterclass. And with this, we close the session of the masterclass in honor of the 80th birthday of Ramon Carbó-Dorca.
Bye-bye. Bye-bye.